Have you ever stopped and thought about what really happens when you flip a switch? Not the light turning on. That part is obvious. But the invisible journey behind it. Because in less than a fraction of a second, electricity travels from somewhere far away through a massive, interconnected system and arrives exactly where you need it. No delay, no confusion, no visible movement. And yet, what's actually happening behind the scenes is far more complex and far more fragile than most people ever realize. Because here's the truth. Electricity doesn't just flow to your home. It's generated, controlled, balanced, and constantly adjusted in real time across an entire network that can collapse if even a small part fails. So the question is, how does it all work? And how does it manage to keep working at all? To understand electricity, you have to start far away from your home. Because the moment you flip a switch, the electricity powering your lights didn't just begin at that instant. It was already in motion. In fact, it was generated seconds earlier at a power plant, possibly hundreds of kilometers away. And not just one type of power plant. It could be coming from a coal plant burning fuel, a nuclear reactor splitting atoms, a hydroelectric dam using flowing water, or a wind turbine spinning in the distance. Each of these sources generates electricity in a different way, but they all share one critical goal: to convert energy into electrical current, reliably, continuously, and at massive scale. And that scale is hard to comprehend. A single large power plant can generate enough electricity to power millions of homes simultaneously. But here's where things get interesting. Electricity isn't stored in massive quantities the way you might think. It has to be generated almost exactly when it's used, which means the system isn't just producing power, it's predicting demand. At every moment of every day, grid operators are performing a delicate balancing act. They must ensure that the amount of electricity being generated exactly matches the amount being consumed. If too much electricity is produced, the system becomes unstable. If too little is generated, parts of the grid can shut down. And this balance has to be maintained in real time. Think about that. Every time millions of people turn on lights, plug in devices, or start appliances, the system must respond instantly. But how does it know? The answer lies in data. Power grids constantly monitor usage patterns. They know when people wake up, when businesses open, and when cities go to sleep. Demand spikes in the morning. It peaks in the evening. It drops late at night. And based on these patterns, power plants adjust output continuously. But there's a problem. Not all energy sources are predictable. Renewable energy, like wind and solar, adds a new layer of complexity. Because unlike traditional power plants, they can't be turned on or off whenever needed. The sun doesn't always shine. The wind doesn't always blow, which means energy supply can fluctuate unpredictably. So how does the system handle that? It compensates. When renewable output drops, other power sources ramp up. When there's excess energy, systems redirect or reduce production. And in some cases, energy is stored temporarily using batteries or other technologies. But even with these solutions, the system is constantly adapting because electricity demand doesn't wait. And this leads to something even more fascinating. Once electricity is generated, it has to travel. The electricity leaving a power plant doesn't go straight to your home. First, it enters the transmission system, and this is where scale becomes almost unimaginable. High-voltage transmission lines stretch across entire countries. Massive towers carry electricity over mountains, rivers, and cities. But here's the key detail. Electricity is transmitted at extremely high voltages. Why? Because higher voltage means lower energy loss. When electricity travels long distances, some of it is lost as heat. By increasing the voltage, the system reduces these losses and makes transmission more efficient. So before electricity leaves the power plant, transformers step up the voltage to extremely high levels. And then, it begins its journey across the grid. The power grid isn't a single path, it's a network. A vast, interconnected web of transmission lines, substations, and distribution systems. Electricity doesn't follow a fixed route. Instead, it flows through multiple possible paths, constantly adjusting based on demand and conditions. It's similar to traffic on a highway system. If one route is congested, flow shifts to another. But unlike cars, electricity moves almost instantly, and that's where things get complicated, because controlling something that moves at near the speed of light requires precision. Grid operators don't control individual electrons. They control the system as a whole. They manage frequency, voltage levels, and load distribution. And one of the most important factors is frequency. In most countries, electricity operates at either 50 or 60 hertz. That means the current alternates direction 50 or 60 times per second. If the frequency drifts too far from its target, it can damage equipment or cause outages. So the entire grid must stay synchronized. Every generator, every line, every connection, working in harmony. And this synchronization happens across massive distances. Eventually, electricity reaches substations closer to cities and neighborhoods. Here, something important happens. The voltage is reduced. Because the extremely high voltages used for transmission are too dangerous for everyday use, transformers step the voltage down to safer levels. From there, electricity enters the distribution network. This is the system that actually delivers power to homes and businesses. You've probably seen it without noticing. Power lines along streets, utility poles, underground cables. This is where the final stage begins. As electricity gets closer to your home, the voltage is reduced even further. By the time it reaches your house, it's at a usable level. It enters through service lines connected to your building. Then, it passes through your meter, which tracks how much electricity you use. And finally, it flows into your electrical panel. From there, it's distributed to outlets, lights, and devices throughout your home. All of this happens in an instant. No waiting, no delay. But here's something most people never think about. The electricity you're using right now was generated just moments ago. For something so fast and seamless, the system is surprisingly fragile because everything depends on balance. A sudden surge in demand, a failure at a power plant, a damaged transmission line. Any of these can disrupt the system. And when that happens, the effects can spread quickly. Blackouts don't just happen in one place. They can cascade. One failure leads to another and another until large parts of the grid shut down. That's why protection systems exist. The grid is constantly monitoring itself. If something goes wrong, automated systems react instantly. They isolate problems, shut down sections, redirect power, all within fractions of a second. These systems are designed to prevent small issues from becoming major failures, but they're not perfect because the grid isn't just a machine. It's an ecosystem. Electricity networks behave more like living systems than mechanical ones. They adapt, they respond, they evolve over time. And just like any ecosystem, they depend on balance. Too much stress, and the system struggles. Too little flexibility, and it breaks. Which is why modern grids are changing. As energy demand grows, the grid is becoming more complex. Renewable energy is expanding. Electric vehicles are increasing demand. Smart devices are changing consumption patterns. To handle this, grids are becoming smarter. Using sensors, automation, and AI, they can predict demand more accurately, adjust supply faster, and respond to problems more efficiently. But this also introduces new challenges. Modern power systems rely heavily on digital infrastructure, control systems, communication networks, software, and with that comes risk. Cyber attacks, system failures, data disruptions. Protecting the grid now means protecting both physical and digital systems. Because in today's world, electricity isn't just about power, it's about information. So the next time you flip a switch and the light turns on instantly, remember what's really happening. Electricity didn't just appear, it was generated, balanced, transmitted, transformed, and delivered across a vast interconnected system. A system operating in real time, a system that must stay perfectly synchronized. And despite everything, it keeps working.